Hello everyone, I am Karunakar from EC department. In this video I am going to discuss about piecewise linear transformation functions. Previously in the classes we have seen some transformations like image negatives, log transformations, power law transformations, etc. So these piecewise linear transformation functions are a quite complementary approach to those functions. The principal advantage or main advantage of these functions or transformation functions over other functions is that the form of piecewise functions can be arbitrarily complex. In fact, we can see a practical implementation of some important transformations can be formulated only as piecewise functions. But we have some disadvantage of this piecewise linear function is that their specification requires more user input. One of the piecewise linear transformation function is a contrast switching. So why we require is this contrast stretching is whenever we take an image there may be some chance of getting a blur image or a low contrast image. That may be because of pure illumination or lack of dynamic range in the imaging sensor, or sometimes even because of wrong setting of lens aperture. So because of these reasons, or among one of those reasons, we may get a low contrast image. So in order to improve the contrast of image or to enhance the contrast of an image, we use this contrast stretching. So simply it is a image enhancement technique that attempts to improve the contrast in the image by stretching the range of intensity values. We can see the figure 3.10. So basically it shows a typical transformation used for contrast stretching, and the locations or points R1, S1 and R2, S2 will decide the it will control the shape of transformation function. So let's say for example if R1 equals to S1 and R2 equals to S2, then the transformation will simply be a linear, so that will not change the input of an image. And the other case is when if R1 equals to S1 equals to 0 and S2 equals to L minus 1, then the transformation will become thresholding function that will create an image binary image. So here in the figure 3.10 you can see this is a figure A where it will show the form of transformation function, and in figure B this is a original low contrast image, and C is the result of contrast stitching, and D is the result of thresholding. Basically it is a binary image. So previously in the below slide we have discussed the two cases of uh, no change or a linear transformation, and the other is a thresholding function. So in figure D we can see the binary image that will result because of thresholding function. Intermediate values of R1, S1 and R2, S2 produce various degrees of spread in the intensity levels of output image, thus affecting its contrast. In general, the point R1 will be less than R2 and S1 will be less than or equals to S2 is assumed, so that the function will be single valued and monotonically increasing. And this why we require this condition is that this condition will preserve the order of intensity levels, thus preventing the creation of intensity artifacts in the processed image. And in the figure 3.10b, here we can see a 8-bit image with low contrast. So this is a P, which is a low contrast image or the original low contrast image. It is a 8-bit image with low contrast, and figure 3.10c. So this is the C. It is a result of contrast stretching obtained by setting R1S1 as R minimum 0 and R2S2 as R max, L minus 1, where R minimum R max denote the minimum and maximum intensity levels in the image respectively. The transformation function stretched the levels linearly from their original range to the full range 0 to L minus 1. So basically the original image will be having the low set of intensity values. Then by stretching those intensity levels we can broaden the range of intensity levels. Finally, figure 3.10t shows the result of using threshold function, which we have defined previously as R1 S1 equals to m comma 0 some m, and R2 S2 as m and L minus 1, where m is the mean intensity level in the image. Yeah. So the original image on which these results are based is a scanning electron microscope image of pollen magnified approximately 700 times. So this and the other type of linear transformation or piecewise linear transformation function is intensity level sizing. Here we will highlight a specific range of intensities in an image. Applications include enhancing features such as mass of water in satellite imagery and enhancing flaws in X-ray images. This process, often called intensity level slicing, this can be implemented in several ways, but we basically will have two basic themes. One of the approach is to display in one value, say white, all the values in the range of interest, and in another, say black, in other intensities. So this transformation shown in figure 3.11a. So we can see in the figure 3.11a basically produces a binary image because from A to B the output intensity values are very high, and from remaining all other intensity values it is low. So basically it is producing a binary image. The second approach is based on the transformation in figure 3.11b. So it will brighten or darken the will darken or brighten the range of intensity values and thus not affecting the other intensity values. In figure 3.12a we can see a aortic angiogram near a kidney area. The objective of this example is to use intensity level slicing to highlight major blood vessels that appear brighter as a result of an injected contrast medium. So figure 3.12b shows the result of using a transformation of the form in figure 3.a with selected band near the top of scale because the range of intensity is brighter than the background. So by applying the transformation of so-called 3.11a, this transformation to the image 3.12a, that will result to the image of 3.12b. So result of using a slicing transformation of the type illustrated in figure 3.1a with range of intensities of interest selected in the upper end of the grayscale. So the result of this transformation is that the blood vessel and parts of other kidney appear white. So it will appear white, and while other intensities are black, this type of enhancement produces a binary image and is useful for studying the shape of the flow of contrast medium or to detect blockages. And in the other hand, the interest lies in the actual intensity values of region of interest. So we can use transformation in figure 3.11b. These transformations, like we increase the intensities to our interest of range of interest, and in other intensities the image will not change. So figure 3.12c, we can see this image 3.12c. So it will show the result of using such a transformation in which band of intensities in the mid-gray region around mean intensity was set to black, while other intensities were left unchanged. So we can see here in these portions, like so these portions became black, and while the other region remained same. Such a result might be useful when the interest lies in measuring the actual flow of contrast medium as a function of time in a series of images. The type of piecewise linear transformation is bit plane slicing. Pixels are digital numbers composed of bits. For example, the intensity of each pixel in a 256 level grayscale image is composed of 8 bits. So that is 1 byte. So instead of highlighting intensity level ranges, we could highlight the contribution made to total image appearance by specific bits. For example, we can take figure 3.13 as it illustrates. It is an 8-bit image considered as being composed of 8 1-bit planes, with plane 1 containing the lowest order bit of all pixels in the image and plane 8 all the highest order bits. Higher order bit planes contain a significant amount of visually significant data. So yeah, in the figure we can see that that image will be composed of 8 bit planes, and bit plane 8 is the most significant bit plane and bit plane 1 is the least significant bit. and we can recreate the original image by using the most significant bit planes. Figure 1.3.14a shows a 8-bit grayscale image, and figure 3.14b, this figure, shows through 1 or its 8 1-bit planes. So this is the original image, and 1 2 3 4, these below images are bit planes of this original image, and this is the lowest order bit and this is the highest order bit, and we can recreate this original image by using the most significant bits. Thank you.